Used to be there was some combination of buttons I could press up here that would turn these lights off, and I can't seem to find it now. So I apologize. Can the folks in the back hear me? Yeah? Okay. All right. So a couple of quick announcements. We now have in our possession what we believe to be correct AWS codes for everybody. So we'll get that out today, Bhuwan, you think? Yeah, okay. But definitely soon. As people know, the deadline was Thursday, and that required doing an AWS run. So we're extending that. It's now Sunday, midnight Sunday, I think. So that gives you some time. Any questions? Is there a question? Okay. So project deadlines. If you're an 805, or if you're interested in doing a project with 805 students, you should look at the wiki. I've now posted deadlines for the project. The first one's not too far off. The end of September, I'm asking you to do an initial proposal. And at the time of the initial proposal, you should have the data set you want to work with. You know, heads up, look at that now. So the wait list, okay, as you can see, drop ads are over. This room's getting a little bit emptier. It still looks like there are 28 people on the 605 wait list and 10 on the 805 wait list. I'm not sure if these people are real or not. I mean, in a sense, I think they're probably real people because they have Andrew IDs, and that's hard to do. It's hard to spoof. It's harder to spoof than a Twitter thing, much more expensive. But I'm not sure if they're really interested in the course or not. So I'm hopeful. Is there anyone in this room that's still on the wait list? Okay. So that's a small number. So I'm hopeful that people, and actually I think there are like a couple of slots that I can add. So we're getting close to clearing the wait list. Just a reminder, if you're on the 805 wait list, okay, and you're not a PhD student, which means that in the little, course database, your class doesn't show up as a 20, then you need to contact me and get my approval. You need to send me a CV. The CV is for taking 805 if you're not a PhD student, okay? So if you haven't been moved off the 805 waitlist and you're a master's student, that may be why, okay? I have no offer hours or office hours next week. I'm gonna be out of town Monday, so we'll just have to sort of struggle with the, 7 TAs that you've got. Okay, so that's it for announcements. Are there any questions about administrative things? Yes? Oh, you don't have an open cloud account yet?
Yeah, I haven't received the email.
Send me an email and I will forward it to the right person. As I said last week, there are a small number of people whose emails bounced. There's at least one person who it got spam foldered or something and they never got it. So you should contact me. You should definitely have that account. Okay. You're registered for the class or on the wait list? Okay. But everyone should have the open cloud account. Okay. So a couple of people have said, well, this last assignment isn't really satisfying because we're not really doing classification at the end. And this was also a question that someone raised. If you've built this classifier, so you have all these event counts, and you can't load them in memory because there are too many of them, how do you actually use them to classify documents? And I gave sort of like a hand-wavy answer about something you could do. If you believe the test set is small, you could use this pipeline to just load the part of the classifier you need. So then you have to scan through the classifier once and pull out the weights that are appropriate for that test set, and then classify the test set. This assumes that the test set is small and the test set fits in memory. So you can use it to evaluate your classifier, but it really doesn't quite scratch the itch. Really, we'd like to be able to run this classifier on a huge set of test documents, okay? So one question is, how can we do that, all right? So just to give you a little bit of background on where we're going next in this course. So far, we've talked about the kind of underlying technology behind Hadoop and MapReduce. Okay, so we've basically told you, what it looks like, how you can visualize this as sort of like a streaming process, why you want to do it, and we've gone through basically one very simple algorithm. Okay, so this is not hard. If I break things down into MapReduce steps, then everybody in this room could probably have already done the assignment of implementing those MapReduce steps with a little bit of extra, study. The hard part about MapReduce is figuring out how to use it when you have an algorithm that needs to be decomposed into a bunch of MapReduce steps. So the hard part is basically using that as a primitive when you're coding, right? Not, choosing a particular, not implementing a particular primitive that somebody's already kind of broken out for you. So this is harder to teach. The only way I know how to teach it is basically to go through a bunch of examples, all right? So I'm going to be basically going through a bunch of examples of this for the next few lectures. So these are all going to be algorithms of various complexities that you're going to break down into MapReduce steps, all right? And we're going to start with the missing piece for our naive Bayes, which is the classification step, all right? So what I've got is I've got test data, I've got document IDs and a bunch of words on each line, all right? And we can assume this is like the key of a record, and that string of text is the value. And I have my event counts. So I've got the name of an event and a number, okay? So this is what I have. These are both too big to put in memory, all right? And what I want to do is I want to classify, all right? So what I'd like to do is I'd like to take all this information and shuffle it around appropriately so I can classify in a streaming process. So maybe what I'd have is I'd have a document. So this is this first test document up there, okay? And I've got all the counters I need for that document right here locally with it on the same line. So this isn't the key value split. I just want to say basically I've got a line that has all this information from here and all the appropriate information you need. Okay, so a bad idea would be to take each line here, scan through all the event counts, right? Pull out exactly what you want for this line, right? Then go to the next one. And so you'd basically be scanning through this, for every line in the test data, right? That's low memory, but it would be ridiculously slow. So we're going to have to do something smarter than that, okay? So I'm going to walk you through what we're going to do, all right? So here's the step that we're going to start with, okay? So what we have here is we have words, and what I'm going to do is I'm going to take these event counters and I'm going to reorganize them. So the key is not the name of the event, but the word that appears in the event, all right? So how do we do this? Okay, so this is what I'm trying to get. I'm trying to get a word and then a list of all the counters that appear for that word, okay? So this basically means the word is aardvark. It appeared twice with sports. The word is agent, and it appeared 1,027 times with sports and 564 times with world news label. Okay, so this is what that record means, right? I'd like to construct a table where the keys are words and the values are these little records of events, related events. Okay, so how can we do this? Actually, not too hard. Okay, we can do a stream and sort. We go through all this. All right, for every one of these things, what we would do is we would print out the word and then the counter. All right. So I'm just focusing now on the kind of the hard counts, the ones that have to do with the words, joint events for words and counters, and the rest of it is like all just details. So we're going to have the word and the count of that number of times that word appears with event. All right. Then we sort that. All right. And we stream through and do a reduce step. And what we're reducing here is building a list of these things. Okay? All right? So this is just like the inverted index program that I showed last week. Very simple idea. We're just going to reduce. Instead of adding things up, we're going to concatenate them in a list. All right? So if I do that, that's basically one stream and sort algorithm here, step here. Or if you like, it's one map reduce algorithm. all right? And that will get us what we want, all right? It will get us a word as the key and the list of related events as the value. All right, so that's the first step, okay? So if I had those things and I could just put them in a database, I'd be done, all right? I could just go through the test data, okay? And for every test case, I would just look up the event counters I need from the database, right? I've got the word, so those are just keys in the database. I could just pick them up of the database, retrieve them, then I could classify using those answers. I'm assuming I can fit a document in memory, so I can fit one of these lines in memory. So of course I can also fit all the counter values in memory, assuming I don't have too many classes, okay? So if I could just do this quickly in a database, then I'd be done, all right? But of course, I'm assuming I don't want to use a database because seeks, and I can't load this into memory because it's too big, so I'm going to have to do something different, right? So it turns out there's sort of a design pattern that you can use for stream and sort programs, MapReduce programs, that basically emulates this, all right? So it's a simple little trick. So what I'm going to do is conceptually, I'm going to go through this and I'm going to issue requests for every event counter, okay? And after those requests get answered, I'm going to do the classification step. So what does this request and answer process look like? Well, of course, it's going to be another sort of stream and sort type operation, all right? So we're going to use the stream and sort machinery that we already have to do this request and answer pattern. We're going to go through here and we're going to generate for each one of these documents a stream of requests, okay? So the request is going to basically tell you the word that you need to classify that ID and the ID that sort of contains that word, okay? So you're going to basically generate these things that are called requests, and the information each request has is the word that you're requesting the accounts for and the ID that needs that word. Okay, so for example, you know, it might look something like this if the first document is found an aardvark in Zynga's Farmville today. I spelled aardvark wrong. Let me get these slides right. Okay, so the first thing would be found. Maybe this is a stop listed thing, so we can skip it. But the next one is aardvark and so on and so forth. The last request is today. Those are all the counters you need for ID 1. Okay, so we could just print these strings out. Just like we printed out our increment requests for the downstream process. I'm going to suggest we do it like this. So found, the word is going to be the key, all right? And the value is going to have the ID in it. And it's going to start with the special magic character tilde. Why tilde? Okay, so tilde in ASCII is the ultimate character, by which I mean it's the last character in lexicographic ordering, okay? I'm just going to assume everything's in ASCII. I'm old school. I'm like that. If you just run sort, actually the Unix sort by default tries to be smart, okay? It tries to sort things in some sort of like clever regionalized way. If you want to turn off its intelligence, then you can just basically say, I want to like, you can set this, this flag, this environment variable, and then everything that sort does will basically just be sorted by lexicographic ASCII thing, which basically means that all these values are going to be last, okay? So we push these to the end, all right? So why am I doing that, you ask, all right? Well, after I generate all these requests, what I'm going to do is I'm going to take these, and I'm going to take all these event counters, and I'm going to concatenate them together, and I'm going to sort that, okay? So I take all these things, I combine them, and I sort them. So this is conceptually just sliding this over to the left, okay? Don't be confused, I just slid this over to the left here. What I end up with, if I take these event counters and I take these requests, I combine them and sort them together, and I end up with something like this, okay? So, so first I'll see the key for aardvark, then I'll see its counter. And then I'll see all the requests involving aardvark, okay? And those will follow the counts because, you know, they're lexicographically after it because I put that little tilde in front, okay? So I've controlled the sort a little bit. So if we look at something like agent, then I'll see first the event counters, then I'll see this long list of things. Okay? So that's the next step in the process. Okay? So now I basically have, in a convenient way that I can stream through. Yeah, question?
Do we do this for every test document?
You do this once for all the test documents.
So you collect the set of words?
Exactly, right. So you're going to go through all the test documents. I've just written one of them here, okay? But we'll have, thousands of requests, or, millions of requests, every word in all the test documents. So we'll have this huge pile of requests. I'll have this huge pile of event counters. They all get sorted together. Okay, good clarification question. Okay. And now I've got this sorted list, and this is sort of convenient to stream through. Okay. So what I'm going to do is I'm going to do another streaming process, and this is going to basically generate the answers to these requests. All right. So this is going to go to another little piece of logic. All right. So what we're going to basically do is the following. Okay. I want to scan through everything. When I reach one of these blocks, the blocks for like the same key, I know the first thing is going to be the event counts. Okay. So when I enter a new block of for a single word, the first thing is always going to be event count. I just grab that, I store it. Okay. So that's the answer for that, for all the requests for that. Okay. And then if it's not the event count, it's going to be a counter. Okay. So if it's not the first thing, it's going to be one of these requests for counters. And I'm just going to answer it. And how do I answer it? Well, what I'm going to do is basically send another message out. Okay. And the message is going to look like this. So I'm going to figure out what the ID is. And I'm going to print out a new value where ID is the key. And the value is this little tilde counter for request is record. Okay. So just to make that concrete here, the output of this for this aardvark thing, basically, there's only one guy that's asked for it. Okay, so I'd say for ID1, the counter for aardvark is this. Okay, and then I'll go through it all further down, and when I get down to this thing for Zynga, again, there'll be something that goes to ID1. All right, the counter for Zynga is whatever it is. Okay, whatever that value is. All right, and again, we're going to get many different IDs here in the output thing. So basically, every message, every test document that asks for a word is going to get some messages back. Question?
What about the different counters for the same word? Do they get concatenated?
Yeah, so they've already been concatenated in the previous step. Okay, so that's why I put them all together. Okay, so you can imagine combining those two things in sort of one process. That might actually be a little bit faster. So that might be an interesting optimization, but I didn't do it here. I'm just trying to keep things conceptually clean.
Also, can you probably store the most frequent words in a faster memory and use that for quicker retrieval?
So the question is, can we store things in memory and sort of speed this up? And yeah, absolutely yes, right? So again, this is sort of the simple way of doing it. Right, so it's sort of like the low memory, the zero memory approach, right? And if you want to think about ways of optimizing it by, caching things out, then you're not required to do it, anytime in the next couple of weeks, but that's a great thing to think about, and it will help you understand this, I think, to think through those things. Okay, all right. So now I've got all this stuff, and once again, I'm going to combine and sort. All right, and I'm going to combine it this time with all the test documents. All right, okay. So I've got this bunch of request answers here. Okay, so the key is an ID, and then I've got basically a little string which basically says here's the counter, here's the value of some counter that you requested. Okay, so we take all these things, we combine them and sort them. And what do we get? All right, we get something like this, okay? So the first thing that has the key of ID1 in any block, all right, whenever I have a continuous block with the same ID. The first thing is always going to be the test document, all right, because it doesn't start with a tilde, all right, and the rest are going to be all the counter values for all the words that appear in the document, right? The first pass through, we asked for all those things, and going through now we found all these things, all right? So we have the test document and all the counters we need to classify it. So what I said we really wanted was something like this. We wanted a row where we basically have the ID, and all the counters for all the words, all right? This isn't quite the same, but honestly, it's good enough, right? I can now just sort of stream through this and do a classification, okay? Does everyone see that? So I can stream through, and all I basically need to do is sort of like keep a running count of the class, the log odds of each class as I process these counters, and that will tell me how to classify each ID. All right? So I gave you pseudocode for a couple of different things here, right? Just kind of scanning back. There's pseudocode for this logic here where we answer a request. There's pseudocode here for generating a request somewhere. Where was that? Maybe I didn't give you the pseudocode for that. But it's sort of clear how to generate a request. And now we've got this, and we can finally go through and classify it. So I'm going to run through this one more time. Okay, so this is the way you might implement it, right? In stream and sort, not in Hadoop. Okay, so first we go through and get the event counts. That was, 1A, homework 1A. The next thing I do is I take those event counts, all right, and I sort them, of course, and I stream through them, and I convert them into this format. Well, let's see. First I got the train, then I've got the counters. The next thing I do is going to convert them to this format where I've got a word and then all the counters for that word. All right. Okay. So that's sort of the first step, this reformatting of the things, and that's basically one MapReduce process after, well, it's two MapReduce processes, one to get the counters and one to group them. All right. Then I'm going to go through and I'm going to generate all the requests. That's this program right here. Okay. So that will generate all the requests, and then I'm going to concatenate that with the words, this file here, and then I'm going to sort that. So cat dash basically means use the standard input as one of the files you're concatenating. Okay, so if I do that, the output, we've got the requests here, we've got the words here. Okay. So those things get concatenated. We get something like this. So this is the input to the answer word count requests program. All right. And when I generate that, I'll take its output, which looks something like this. All right. It tells you what the right counters are for every word. We concatenate with the test data. All right. And throw them together, and we have this. Okay. So this is the input of the last step, which is, test naive Bayes using requests, all right? And I won't show you what that looks like, but you can kind of guess, all right? Okay, so does that make sense to people? All right, so the quiz for today, basically, to answer it, you're going to have to kind of step through this process kind of, slowly and carefully. So, it's not complicated, but it's worth doing. Okay, and there is a quiz for today. Okay. So we filled in the missing piece. Now we can do training and tests. We can do it, in a hash table, or we can do it using basically zero memory, doing everything on disk, only using sorts to organize our computation. Okay, which also means I can do it in Hadoop with a low memory machine. All right. So like I said, what I'm going to do over the next few lectures is basically talk through a bunch of algorithms. So this one I talked through in a lot of detail. I'm going to talk through another one in a little bit less detail. So before I move on, are there questions?
So far in the testing case, did we use the hash table library?
In this testing here?
Yeah. Maybe
Yeah, so homework 1A basically said you could put things in a hash table, you load them in memory, so then you can stream through the test data and just classify it.
No, I mean in the testing phase, what you just discussed, did we use hash table in memory?
Right, so we'll use constant memory, okay? It's a little bit larger constant, right? Because when you're going through, what you're going to store is you're going to store all the event counts for a word. So you'll have one event counter for every class. So if there's like 17 classes, there'll be 17 counters. So but all you have to keep in memory when you're generating the requests and when you're answering the request, it's still sort of like a finite amount of space. So it's a finite amount. It's basically one line in these formats that I gave you. Okay. Okay. So Rocchio's algorithm. We talked about this a little earlier on as another example of a very kind of streaming low memory algorithm. This is the specification for it. So the DF is the document frequency of a word, the number of documents it appears in. TF is the number of times it appears in a document. There's this formula IDF, which is roughly the inverse of the document frequency. And then there's this other formula which gives you a weight for a word in a document. So there are lots of variants of these formula. And now if I look at, if I take a vector, which basically gives me for each document the weight of every word in that document, right there. Okay, that's called U of D. All right. And I can basically construct a vector which corresponds to a class by constructing the centroid of these. So if we drop away this B stuff, I'm basically just averaging the vectors of all the documents in that class. All right. And then finally, at the end of the day, I just look at the max of these things here. So basically, I'm looking at the document. I'm looking at the class vector that's most similar to the document vector. Okay. So this is the basic algorithm, very concise and easy to describe in math. Okay. And this is a specification for the algorithm. If we want to implement this at scale, we might have to do a little bit of work to make this efficient, right? If I want to do it in MATLAB, I'm basically done. Okay. But if I want to do it at scale, I have a little bit more work to do. So it's convenient to introduce this extra thing here. So V of D is just the document vector for D normalized. So this is the 2 norm. So we're just normalizing it by its Euclidean length. All right. And the same thing for V of Y. That's just a normalized vector. And now the formula I'm using to score a document, with a class is just dot product. So it's a very simple formula at the end of the day. Okay. So this is sort of a nice, concise description of the implementation. So let's think how we would do this. All right. So in naive Bayes, I basically had this sort of process. I had training data. I had event counts. All right. And then I went through this tortuous process of requests and answers and counts, shuffling things around on disk until I got everything where I wanted it. All right. So I'm constrained to use these low memory stream and sort, Hadoop map reduce sort of operations. So that sort of limits how I'm going to do things. But we figured out a way to kind of get the right information, to get all the information we need in one place. All right. So this is kind of what we want to do here. All right. So there's one extra. There's basically. So for Rocchio, what you need to do, you don't have this notion of event counts, right? Instead, what you need to use is you need to use the document frequencies. All right. So every word has a document frequency. That's used in the formula you're using to construct the Ys, the vectors for each class. And it's used in the representation you're going to construct for each document. So it's used for V of D. So you need to get that information and bring it to the same place as the training data, which tells you what words are actually in the document. All right. So what we'd like to do is, for naive Bayes, we basically wanted to take the document and collect all the event counts for that in test phase. All right. Here in training phase, we want to do something similar, right? We want to basically take this document and we want to get the V weights for every word in that document. All right. And to get those, we need the DF counts. All right. Okay, so that's the basic goal, all right? And it's really the same problem we saw before, except we're actually starting a little bit further ahead in the game. So with naive Bayes, I had to first do some fiddling around to get a table that was indexed by word. Here, the table's already indexed by word. I've already got the document frequency for each word, okay? So instead of doing this process where I request the event counts for a word, I'll just do the same sort of process, but I'll request the document frequency, okay? And when I get that going through here, once again, I can take this combination here. I've got, well, let's see. At the end of the day, what I'm going to have is I'm going to have this representation of each document. Okay, so after I merge the information from the document frequencies in, I can get all the appropriate weights for each word, just like I had the event counts for each word in naive Bayes. All right, and now I can use that to do the next step of, which is training the classifiers for Rokio. All right, so to train the classifiers for Rokio, basically what I have to do is I have to average out the classifiers for each document. All right, so we're averaging a vector, so we have to put in the appropriate update to every non-zero component of that vector. So I go through the non-zero values, all right, which are just the ones that are explicitly stored here, okay? And I want to increment some counter, all right, for that dimension. Just like naive Bayes, I don't want to assume that can fit in memory, okay? So again, this is another map-reducey sort of process, and it's something that we've seen before. We saw this when we were constructing the event counts in naive Bayes. What we basically have to do is go through, these lines, okay, once we've constructed the actual weights for each document, all right, and we'll send out a little message which basically says, well, you have to increment the appropriate component, the one for the word, each particular word that appears in that document by some amount, all right? The amount you're incrementing it turns out to be the weight of that word times alpha divided by the number of words for that in that class. Okay, so you're going to emit a whole bunch of increment terms like this, and then once again sort them, reduce them together so we get a total weight. Okay, and that's basically the process. Okay, so when we're done with that, which is, again, this is using two things we've seen before. It's just slightly different orders, okay? We took a table of information about individual words, and we took a test corpus. We merged that together, in this case, to get the TF-IDF representation of every document, all right? Then we went through that representation. We streamed through that to construct our classifier. By doing a bunch of, by doing a map reduce step where we basically add up weights, all right? And now at test time, again, I've got something very similar to what I had before. For every word, I've got its weight in each of the class vectors, all right? So that's its weight for classification purposes, all right? So this is, again, isomorphic to the test process for naive Bayes. I have to take this information and shuffle it around, so I get not just the document vector for each word, but the appropriate components of the vector for each class, right? So the components for all the words in that document, all right? And once I've got that, then I can just look at this and I can compute the dot products and figure out what the class is, all right? Question?
Can we modify this algorithm for n-grams rather than just bag of words?
So can we use this algorithm for n-grams instead of just bag of words? You can. It's actually pretty easy to modify all these things. I mean, in fact, you could do this by starting at the very beginning, okay? So when you could scan through your corpus, right, and replace the bag of words that represents a document with a bag of n-grams, right? And then everything's the same. Right. Okay. So again, Rokio. So to compute the document frequency, I didn't tell you how to do that. You could figure it out. Okay. You got to scan through the corpus. It's kind of like the naive Bayes event counts. All right. It's basically easy to do if you assume you can load every document into memory, because then you can just take the document and you can eliminate duplicates in that document locally, right? And then just output a counter, an increment for each document that appears at least once to increment the document frequency. All right. Then we're going to compute the TF-IDF representation of every document. All right. Okay. So if you could put all the document frequencies in memory, you could just do it with a scan, right? Otherwise, it's basically like part of the naive Bayes test procedure, okay? And the last step is we got to add up the vectors, okay? Right? So that's basically one scan. Again, if the v of y's fit in memory. Otherwise, it's basically like naive Bayes training step, okay? So this classification, and then the classification process is pretty much just like the naive Bayes classification process. All right. So it's a more complicated algorithm to write down in MapReduce, but it's another algorithm where order of the examples doesn't matter. You can do it with sort of a fixed number of scans through the data. So it's also a very, very efficient algorithm. So one thing that's kind of nice about this algorithm, okay, as well as naive Bayes, if you kind of think about it. So you can parallelize this. We can take these documents and we compute the document frequencies, right? So we can do this in parallel in a MapReduce step and combine all these things to get a single set of document, a single document frequency table. All right. And then here I've got to take that, and when I'm doing my next stage where I'm computing the v of y's, all right, I'm going to basically need to take this information and kind of merge it in, right? So what's nice about this is that when you're accessing these DFs, you need a copy of these document frequencies everywhere you go, right? So if you were doing this, you'd have to take the entire document frequency table and have it available for everybody, okay? But you don't need to write that access. You only need read access, all right? So if we had something where we could sort of store the document frequencies in memory, okay, and we still want to compute them with many disk drives, we can imagine first doing this scan here to get all the document frequencies, then copying them to each one of my worker machines, all right? And then in the map phase for my worker machine, when the map phase starts up, I'd load those document frequencies into memory, okay? So if the document frequency table is small enough, then that would be faster than doing additional disk scans, all right? And the nice thing about this is I only have to read these things. So I don't have to worry about keeping the document frequencies in sync. They never change, all right? If I had to share some statistics on every word, but those statistics changed over time, it would be a totally different problem. So that's another thing to kind of think about. This is it's a case where we've got this common information, but it's information that's not shared, all right? And that's another thing that makes this process efficient. You guys still hear me out there? I feel like my voice is getting a little bit hoarser as the lecture goes on. Okay. So if the TAs are listening, this would be like a good midterm exam question, just to like sort of like step out the, lay out the steps for like Rokio. Don't tell the students that. I thought it was a good idea though. All right. Okay. So probably what you're thinking right now is, this is very detailed. I think I get the idea, but boy, is it going to be tough to be paying attention to this level of detail for algorithms for like the next 2 or 3 lectures, right? I really wish I'd gotten more coffee, right? Note to self, get more coffee for my next lecture. All right, so I'm going to help you out a little bit here, okay? And we're going to introduce some abstractions that let you talk about these things a little bit more succinctly, all right? So request and answer is sort of a good low-level operation. And if you're writing a MapReduce pipeline sort of kind of on bare metal, as you may well do if you're trying to make something go fast, it's a really good thing to know. But when you're designing algorithms and when you're prototyping things, it may not be the level you want to work at, okay? So let's introduce some sort of high-level things, okay? So let's think for a second about some of the things we've done, all right? And let's think about how we could express these operations concisely, all right? What could we do to make it a little bit easier to write this stuff down, all right? So are there some special cases of this MapReduce process that we can parameterize and reuse, okay? So here are some obvious things we can do. If we're streaming through a table, we could obviously take some operation on every row of the table. So we could go through a table and transform that row and output the result, okay? So an example of that, I mean, maybe I want to go through and I want to stem all the words in a stream of word count frames. So I've got document frequencies, and I want to basically, change the word to a word stem. Or maybe I've got a bag of words, and I want to, or a list of words, and I want to change it from a bag of words into a bag of n-grams. Okay, so basically we're going to go through every process, everything in the table, and transform it. So here's a proposed syntax, right? So so we've got some function which takes a row as an argument. All right, so f is just this arbitrary function. Or more exactly, this little lambda expression just describes this arbitrary function. How many people have seen something like this? Okay. So the syntax will basically, table 2 is just going to be mapping this table using this operation. Okay. Here's another thing that would be pretty simple to do. Decide if you want to keep something, and if you don't, throw it away. So maybe I want to throw out stop words from my table. Okay. So we could also have like an arbitrary filter operation that takes a function which returns either true or false, okay, and just filters that. Okay? So those are kind of some simple things to do. All right. Here's one that actually turns out to be pretty useful, but might not be something you'd kind of think up off the top of your head like in the first 10 minutes. An example of this would be like maybe tokenizing a line. Okay. So I've taken each sentence and I've constructed a list of tokens, okay? But at the end of the day, I want to basically have one word for row, all right? So there's an operation called flatten, okay? So what I'm basically going to do is for every row, I'm going to generate a list of things, okay? And then I'm going to basically append all those lists, elements of the list vertically, okay? So if I flattened these two strings, or these two entries, okay, and my map is basically, and the lambda expression here basically just as tokenizing, then I'll end up with just a list, an ordered list of all the tokens, one word per row, okay. That's another useful thing to do, okay. Oh. Crap. All right. So just to describe how we might do this in naive Bayes, right? Right. So here's another thing which is not sort of sort of a completely obvious process. So in naive Bayes, one thing I'm doing is I'm taking these event counts here, and I'm reformatting them. All right. So I'm pulling together all the event counts that involve a particular word, like Zymergy, right? So essentially what I'm doing is I'm grouping things together, all right? So here's a possible syntax for that, okay? What I'm going to do is I'm going to take a function which takes a row and returns the key that I want to use to group it by, okay? So here it would take an event and would return the word part of the event, right? And the syntax is I'm going to group table by that function, all right? And you know, the way we define this, you know, this is an abstract level. You know, there actually I'm going to talk about several different concrete languages that let you use these sorts of operations. You know, things like Spark and Pig, and they have different ways of specifying this function, right? So it might be that, you know, this row is some structured object, and there's a notion of a field. It might actually be some function that you use, okay? This is another type of operation you might do, okay? If I wanted to implement this, right, this group operation in general, we've sort of gotten one example of it so far, all right? But here's sort of the way you could do it in general, all right? We could output pairs, okay, where we apply the function of the row to get the key. So we output pairs where the key is obtained by applying that function to the row, okay? And then we, so that's basically our initial process, which is really a map, right? So we're mapping the original row to this pair, okay? Then we sort the pairs by the key, all right? And then I do a reduce where we aggregate things together, all right? So for the group operation, I'm assuming that the output of this is going to be a list of things, all right? So the group we're going to aggregate by appending together all the values associated with the same key, all right? All right, so this is how you would implement this under the hood, but we'll kind of treat this as like a primitive from now on, all right? Okay, here's another example. So we have this request and answer thing, all right? So this is a low-level thing. We can turn it directly into like a stream and sort program. And let's break this down a little bit. So there are really a couple of stages here conceptually. We generate the data that's being requested, okay? So the requests here are indexed by the word, okay? So these are our word-based clusters of event counts, all right? Then we generate the requests, all right? So here, the requests were basically done by mapping and flattening, okay? And then the next thing we're doing is basically to join those two tables, all right? So the way we join those two tables is we basically stuck the keys that we're going to join them by, you know, as keys in our key value pairs. We sorted all those things, right? And then we used the streaming process to basically, you know, produce either the join or the output of the join. But more generally, we can think about joining these things. So conceptually, what a join does is it will do a cross product of two key value pair sets, all right? And then just filter out the pairs that have the same value for each key, okay? So this join operation replaces this concatenating two different tables and reducing them together, all right? So, so we could take this operation here and, whoops, what happened? We can take this operation here where we have words and requests and then words and counters, right? And we would replace it with a join, which has basically every, you know, legal pairing of the counter value and the requests, all right? So if this agent appears many, many times in the request field, we'd have many, many different lines in the join. Okay. So that's another kind of useful primitive to have, okay? And the syntax would be a join where table 1, table 2, and then we just have a function which tells you what the key is. That's my abstract syntax. Okay. So a couple of examples here. We might join the word in the document by the word and the word counters, okay? Assuming we've got, you know, if word is a function that let's see. Okay, word and doc by word counters by word. So word here has got to be a function which returns the key of these things. All right. So here in my abstract syntax, it's just a function here, and that's just the name of the function. All right. If you want to actually put the function in our syntax, so I can use this, but it requires me to actually go into like PowerPoint and like pull out a symbol object, a little lambda, and it's kind of a pain to do. In Python, there's sort of a nice syntax for functions. If you write this little text right here and you apply it to a tuple, then what Python will do is they'll say, okay, well, these are the arguments of your function, right? It believes the arguments of the function are a tuple, and the first thing is going to be bound to the variable word, and the second one will be bound to the value doc ID, and then what you return is after the colon, right? So if I basically had pairs that were word, document ID, and this table, right, and word counters in this table, then I could define my functions this way in Python. So it's very concise and sort of relatively clear. Okay. Yeah.
What's the benefits of using the join operation here instead of what we did before?
The join version.
Yeah, instead of using the sort here. Seems like this join operation is more expensive than what we did.
Well, I haven't told you how the join would be implemented or might be implemented, right? So the join is an abstraction. It just tells you what the output is given inputs, right? So I haven't told you whether it's more efficient or less efficient, okay? It is, in fact, the case that in a high-level language, when you say join, you're probably not controlling exactly how that join is done, right? Whereas if you kind of go down to the level of MapReduce and use request and answer, then you can just really, get in there and nail exactly what's happening. And you can also possibly combine that step with something else. So you have more control over it. And that's one reason for talking about these lower level operations. But there's also a value for having these kind of more high level declarative representations as well. And it just basically makes the code kind of cleaner and simpler. Yes?
Are these joins deterministic given the fact that we might be running this on probably hundreds of machines? But deterministic, I mean, maybe like one machine is completely down with the counters and it's not able to respond, for example.
Yeah, right. So let's see, where am I getting to this? I'm going to get to that in this lecture, I'm pretty sure, okay? So the questions here are basically, how would you do this join, okay? So we're going to get to that pretty soon, all right? Before I do that, I just wanted to give a little bit of an example of how you might use these things kind of in more like a real life situation, okay? So this is some abstract code for constructing a TF-IDF representation of documents, okay? And what I'm going to assume is I'm going to start out with this sort of representation. I just have a doc ID and then a term that's in that doc ID. So everything is a pair with a doc ID and a term that appears in that document. All right. So I'm not starting with a doc ID and then a list of terms. I've already kind of turned it into a bag of words by just constructing these pairs. So this is already kind of my first choice. Okay. And then I've got these operators. I've got map and join. Okay, and then I've got a couple of other operations here. So I've got group by, and then there's some other stuff I'll talk about in a second. All right, and distinct is basically just pulling out, one unique tuple of each kind. All right, so to figure out what the document frequency are, first we can just sort of run distinct on the data. So I basically am throwing away duplicate terms in a document. All right, then I'm going to group by, and I've got this function, right? This is almost the Python code. Of a document ID term pair. Okay, I'm just going to output the term, so I'm just grouping by the term value. All right. And I've got this little operation here, and I'm kind of putting this in with the group or very close to the group because I know I want to optimize this. So I'm going to group by this, but rather than actually construct the list, all I really need is the number of things in the list. So I'm going to say reducing to the count of the things in the list. All right. All right, here's another one. I'm going to map the data. So I've got document ID and term, and I'm just going to map it into the document IDs, and then I'm just going to run that through distinct. All right, so this will give me the distinct document IDs. All right, and then the last thing I'm going to do is the next thing I'm going to do is I'm going to take those document IDs and I'm going to group them together. All right, the key I'm going to use is a constant function, so everything has the same key. All right, and once again, I'm going to reduce it to a count. So this is basically just counting the number of document IDs. All right. All right, so when I'm done here, document frequency is going to be a bunch of pairs that look like the term and a document frequency. And here, this is going to be a pair that's got the key, which is just 1, and the number of documents in the corpus. All right. Now I'm going to basically take this and I'm going to combine these things with the document frequency. So I'm going to take the data, all right. So I've got the data and I've got the document frequency table. All right. The data looks like this. The document frequency table looks like that. All right. So we'll use the same key at term. All right. And at the end of the day, when I do a join, I didn't really say what the output was, but I'm going to assume that what it does is it basically outputs another tuple, right? Where the first thing is, the left argument of the join, and the second thing is the right argument of the join. Okay. So what's output is now a tuple where each thing inside it is a tuple. All right. So I'm going to map this to something a little bit cleaner. All right. Just a triple document ID term and a doc ID, a term, and a document frequency for that term. All right. Okay. And now I can construct my U vector. Okay. So I'm going to join this document frequency, and then I'm also going to join it with a number of documents. All right. And I'm just going to join it by this constant term. So I'm just pulling this document frequency, this number of documents thing into that representation. And then what I've got is I've got these tuples. Okay. So I've got dummy, which is always 1. The number of documents, that's always the second half of my my tuple, and the first half is this little triple. It's got the document ID of the term and the document frequency. Okay, so now I can give you the weighted value of that term in that document. Okay. So this is the document ID, this is the term, and this is the weight before normalizing. Okay. So I could have done this with request and answer. Okay. It wouldn't fit on one slide. All right. It would be a few slides. So there's maybe a little bit of a compression that's going on here. All right. Yeah. Okay. So again, what's going on here? I should really review my slides more carefully. When we do found, ideally what we do is what the group by does without this reducing clause, it'll just give me a list of all the values, or a list of all the rows that contain that value. All right. And reducing here, we're going to basically never omit that big long list. We'll just omit the number of things in it. All right. So we'll have something like this. Okay. And then the number of documents, the key will always be 1, and we'll just have like a list, a number which is the number of documents in the corpus. All right. Let's skip those questions for now. Yeah. Yeah. Okay. And then basically we can do a couple of more operations here. We can group together the unnormalized document vectors. Okay, so the unnormalized document vectors are these triples. All right. I want to divide this by the length of that document vector. All right. So what I'm going to do is I'm going to basically go through this list of things, and I'll just keep one value instead of like constructing a list that has all those rows. I'm going to construct a list which just has the square of the weights. Okay. And then I'll reduce that to the sum. All right. And there really should be, we have one more thing to do because we've got to take the square root of that if I want the Euclidean norm. So I don't have that done yet, but so I've got, at the end of this, I'll have a list of things, which is a document ID and the sum of the square of the weights. And then finally, I'm going to take these unnormalized document vectors, all right, join them with the normalizers, okay, by document ID. So the output of my join is going to look like this: a document ID, a term, unnormalized weight, the document ID, and the normalizer, okay. And then I'm going to basically just take the weight and divide it by, the square root of the norm, which is a normalizer, all right. So this finally gives me a TF-IDF, all right. So that's 2 slides and just sort of a handful of operations. Okay. Yeah, so this is what we'll get at the end of the day. So now the question was, how do you actually implement this, right? Or maybe more accurately, what are the different ways of implementing it and what are the trade-offs, okay? So in MapReduce systems, there are basically 2 fundamentally different ways of doing a join, and they have different trade-offs. So one's called a reduced side join and one's called a map side join, all right? So let's talk about the reduced side join first, okay? So let's say I've got, this join I'm doing here, okay? So I've got document frequencies and I've got the documents that a term appears in. I want to basically join these things, all right? So the way, one way you could do this join is you can just concatenate these tables together. You can sort them, okay? And then you can do that join in a streaming fashion on the sorted data, okay? So if I get all the aardvark things together, okay, and this assumes we might have to do a little bit of buffering, right? I might have to buffer up all the terms, let's say, from one of these 2 lists, right? But if I do that, if I can do that buffering, then I can basically take this sorted list of pairs from both things and construct the join, right? And the join would, let's say, be a pair where the left part of the join is a row from this table and the right part is a row from this table, okay? It's a little bit tricky to do this. So to do this, I'm going to have to sort by 2 different values. So before I had this notion of messages, and I put this little tilde in front so that the messages would be in a predictable order, all right? Here I really want to sort by 2 values, right? So in this case, I really want the document frequencies to come first in my sorted order, okay? Because there's only one of those, and there might be lots and lots of occurrences of a particular term in the corpus, right? So if I'm going to buffer up one set of inputs, then I'd rather buffer up the document frequency because there's just one of them, all right? So what we really ought to do is we ought to take this, and when I do the join, what I ought to do is construct something like this. So first I take these and map them. So my key is something that's kind of in 2 parts. So first is the real key, all right? And then is the source of that key. Is it from A or is it from B? All right, the first table, the document frequency table, or the second table, all right? And once I take these things and sort them together, all right, and if I sort them so that all the A's go first, so the first thing in my sorted list will be aardvark A7, and then aardvark B 2015, and then way down that there'll be another block of things that are called found, right? And there'll be one entry in found from the doc frequency table, and there'll be a whole bunch from the corpus, all right? So I want to sort by both parts of this, okay? But I can't just make the key be found and concatenated with A, all right? And the reason I can't do that is because when I parallelize, I want all the things with the same key to go to the same worker, right? So I want aardvark and A to go to the same worker as aardvark and B. So if the keys are different, that won't work, right? All right, so we're now like sort of in this situation where I want to group things by just this first argument, right? And I want to sort things by the first 2 columns, All right. So in raw Hadoop, there are ways of doing this. Okay. You can do a custom sort where you have a secondary sort key. And you can have a custom partitioner, which basically will say that I'm going to treat all the tuples that have the key of aardvark as the same partition. You can do this in raw Hadoop. It just takes a little bit of extra access to the interface. So you have to write a comparator object and you have to write a partitioner object. If we do that, then we should get the right results in Hadoop. So that's how you would implement a reduced side join in Hadoop. All right. A map side join is actually simpler. All right. Here's the map side join. Okay. So what I'm going to do is I'll take the smaller relation, I'll write it out to disk, then I'll send it out to each map worker. Okay. So just the same way that you can broadcast your code to every map worker, you can broadcast a file to every map worker. All right. The machinery for doing that in Hadoop is called distributed cache. So if you Google that, you can sort of figure out what the mechanism is for that. All right. And then there's in every mapper that you write, the operation that you're used in homework 1B is you just basically you override the map method. So you implement a map method. There are other methods that you can override. So one of them is configure. So configure gets called when every mapper process starts up. All right, and then after configure gets called, map will get called many, many times. All right. So configure is basically the way you initialize a mapper, so you can have the mapper call configure and load in this distributed file. All right. Then we basically just stream through the larger relation using the map process. All right. Whenever I get a new table from the large relation, I just do the join. Right. I've got the values from the small relation, let's say in a hash table. So I just keep the document frequencies in a hash table, and then whenever I'm doing the join, I basically just sort of stream through each thing and output the additional values. All right. So this is much faster than doing the reduced side join. So in the reduced side join, you take both relations, you sort them together, right? And then you do a stream and a reduce, okay? Here, you basically just have to make a pass over one of the relations, right? So if one of the relations is small enough to go into memory, this kind of join is usually faster, all right? So you just have to stream, you don't necessarily even have to sort it. Okay. So this is sort of how we would implement those two operations in raw Hadoop. Okay. Let me stop here. Questions? Anyone? Okay. So just a heads up, Thursday an assignment is going to go out, and the assignment is going to be to write stuff in one of these abstract languages. All right. So according to my calculations, I have about a little more than 10 minutes. And I think actually, rather than jumping further into this, I'm going to let you guys maybe take 10 minutes to review notes or something like that extra. And I'm going to stop now because this is sort of a good place to break things. So I will see you guys on Thursday.